Hi guys, we're doing this chemistry paper today, 9701, paper 42, February March 2023. So the paper isn't officially out yet, so I don't have access to the threshold. So let's begin. Starting with question number 1. By the way, from 2022 onwards, we don't have access to the data booklet, right? So we just have access to the periodic table at the end of the QP along with some data values. So things like, basically uh, oxidation and half equations, basically redox half equations, we don't have access to those. And we also need to memorize the ortho para reacting groups and meta reacting groups. Okay, we had access to that before. Also things like amino acids, the R groups of amino acids, they're going to be given, so you don't need to memorize them. All right, okay, let's begin. Before that, I'm just gonna bring the periodic table from the paper tools that I've solved. Wait up. I have access to the pre-standardized mark scheme, by the way. It isn't the official mark scheme, but it'll do for now. The most common zinc mineral contains zinc 2 sulfide. Complete the electrons in boxes in the box diagram in figure 1.1 to show the electronic configuration of the zinc 2 plus ion. So we have the electronic configuration of argon. So that's 1s2, 2s2, 2p6, 3s2, 3p6. 3p6 is still argon. Then when we go for the zinc ion, what is the usual configuration of zinc? It's basically 4s2 followed by 3d10. You guys know that zinc isn't really a transition metal. It might be a d block element, but it's not a transition metal, because to be a transition metal you need at least one ion that has partially filled d orbitals, but zinc actually has a fully filled d orbital. As a result, it is not a transition metal, so its compounds aren't colored. So zinc is basically the electronic configuration of argon followed by 4s2, 3d10. So what about the zinc 2 plus ion? It has the electron configuration of argon as well. And you know that for transition metals, the when you form a cation, the electrons actually go from the 4s orbital first. So you end up with 3d10 only. So that's the electronic configuration. The 4s subshell is actually empty, as well as the 4p subshell, it's empty as well. So we just have 3d10. So it's going to look like this: 1 2 3 4 5 followed by 1 2 3 4 5. That's all. Complete figure 1.2 to show the Born-Haber diagram for the ionic solid zinc sulfide. Includes state symbols of relevant species. Okay, so we begin with zinc solid over here. So atomization of zinc leads to the formation of gaseous zinc, followed by ionization, first ionization energy of zinc and the second ionization energy of zinc. So we have to fill these blanks up with the proper elements. So here we need zinc solid, which is the natural state of zinc, and we need sulfur. So sulfur does exist as S8 naturally, but for the sake of it, you can just write S solid. That also works, the yellow solid sulfur. Now atomization of zinc, that actually leads to zinc gas. Sulfur is still S solid. This is the atomization, enthalpy of atomization of sulfur. So we are going to end up with zinc gas followed by sulfur gas over here. And after the first ionization energy, we are going to end up with zinc plus gas, and an electron will be released following that, and we still have sulfur gas. And after the second ionization energy, we actually end up with zinc 2 plus gas plus 2 moles of electrons plus sulfur gas. So this is our starting condition. After atomization of zinc, we end up with zinc gas from solid. After atomization of sulfur, I actually misread this the first time, we end up with zinc gas plus sulfur gas, and then you know the drill. After first ionization energy, we end up with Zn plus, and after second IE, we end up with Zn2 plus. So that's all. Describe the trend in the first electron affinity of group 16 elements sulfur. to Te. So let's try to understand this. I haven't seen this question before. This is probably the first time that I've seen this. So we're talking about group 16 elements. You have to answer this with common sense actually, just like ionization energy. As you go from sulfur to tellurium, as you go down group 16, what happened to ionization energy, by the way? As you went down the group, ionization energy actually decreased. The main reason being electrons were added to new shells. So they are further from the nucleus and there's increased shielding. So although nuclear charge increases, there it becomes easier to remove the electron. Now, what about electron affinity though? For electron affinity, we're basically trying to add an electron, right? For electron affinity, we're trying to add an electron to the valence shell. So the first electron affinity is always negative, exothermic, remember that. So it's one type of bond formation. It's not bond breaking. So as you go down the group, think about it. It becomes easier to add the electron, right? Because think about this. This is sulfur, right? Sulfur has 1, 2, 3 shells. What about tellurium? It has 1, 2, 3, 4, 5. 5 shells. So as we go down the group, look at this. We are trying to add, wait, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. We're trying to add this electron to the outer shell over here. So clearly, we are going to, experience attraction from the nucleus as the electron is added. So a bond is formed essentially. However, as we go down the group, there is less attraction for the nucleus, right? Because the nucleus is further away from the valence shell down the group. So there will be less attracting force for the electron. And you know that there is more shielding because there are more shells. So those shells will also try to repel you. So essentially the new bond that is formed as you go down the group is going to be less exothermic, or it's going to be less negative. Since the new bond that is formed, since it's a bond with weaker attraction, it will have less enthalpy. You guys know that the stronger the bond formation, the more exothermic the change. However, as you go down the group, since the distance is increasing, there is more shielding, there is less attraction, the bond formed will be weaker, so the change will also be less exothermic, okay? So as we go down the group, let's talk about ionization energy. Ionization energy decreases down the group. What do we mean by decreases? We know that ionization energy is always positive, right? So it becomes more negative or takes a less positive value. Similarly, for electron affinity, the first electron affinity specifically, it will take a more positive value, or more accurately, it will be less negative than before because the newer bond is weaker due to the lower attraction. Okay, so this is the first time I've seen this question. Actually, I haven't seen this before. So let's write this down. The first electron affinity becomes less negative down the group, or from sulfur to tellurium. This is the first point. For the second point, we have multiple options. You can either say that the outer shell is farther away, the outer shell gets farther from nucleus, or it is at a higher energy level, or there is basically more shielding due to outer shells. So you can give any one of these points. And for the last point, which is compulsory, you have to state that there is less attraction for the nucleus Basically, the electron has less attraction. There's less attraction between the electron, the incoming electron, and the nucleus. So less attraction means a weaker bond, so it's going to be less exothermic, more positive, or less negative, basically. Now, let's move on to the next one. Explain why the lattice energy of zinc oxide is more exothermic than that of zinc sulfide. Okay, so this is a pretty common question. We know this answer. So while comparing lattice enthalpy, we know that we have to compare charge density, basically charge and size. So what do we have? On one hand, we have zinc oxide. On the other hand, we have zinc sulfide. So the cation is the same, so no point comparing that. We need to compare oxide and sulfide. So basically, look at this. Both of them have a charge of 2 minus. It's just that oxide is a much smaller anion, mainly due to having one less shell than sulfur. So it has the same charge but smaller size or radius. So it has higher charge density. So there will be greater attraction for the Zn2 plus cation. As a result, it will be more exothermic. Okay, so that's the answer. That O2 minus has the same charge but smaller radius than S2 minus. Essentially, more charge density. You could say that directly O2 minus has higher charge density. You'd get a mark. Then S2 minus. Fine. What about the second marking point? Basically, there will be a stronger ionic bond or greater attraction between Zn2 plus and O2 minus. So there's a stronger ionic bond or greater attraction between Zn2 plus and O2 minus. Fine. Let's move on to the next one. Zinc metal can be obtained in a two-step process as shown. So zinc sulfide plus oxygen gives you zinc oxide plus SO2. Zinc oxide plus carbon gives you zinc plus CO. The reactions are carried out at 800 degrees Celsius. Predict the sign of the entropy change of the reaction in step 1. Explain your answer. Basically, what's happening? Entropy is basically a measure of disorder, right? But they don't accept this Marxist definition anymore. They will go with the number of arrangements of energy levels. Now that's the answer that's in the syllabus, so you should write that. It's in the paper in October, November 2022. Please check that out. So what happened to the number of gaseous ions? It went from 3 to 2. So there was a decrease in the number of gaseous moles. As a result, del S will be negative because there's less disorder. So del S is basically negative. The reason being, there are more moles of gaseous reactants than gaseous products. Or you could say that the number of gaseous moles decreases, has a net decrease. The reason being, more moles of gaseous reactants than gaseous products. Fine. Use the data in table 1.1 to calculate del S of the reaction shown in step 2. We're talking about this reaction specifically. So it's basically S products minus S reactants. You guys know that, right? Del S of products minus S of reactants. Let's do this. So what are the products? Zinc and carbon monoxide. So that's 50.8 plus 197.7 minus zinc oxide and carbon 43.7 plus 5.7. So let's do this. 50.8 plus 197.7 minus 43.7 minus 5.7. 199.1 joule per Kelvin per mole. Plus, by the way. Next, An equation for the direct reduction of zinc sulfide by carbon is shown. The reaction is not feasible at 800 degrees Celsius. Calculate del G for this reaction. So guys, you know that the formula for del G is del G is equal to del H minus T del S. For a reaction to be feasible, basically del G must be negative. Gibbs free energy must be negative. You guys also know that. So let's find it out at 800 degrees Celsius. So del H, we need to give this in kilojoules, by the way. So that's plus 733 kilojoule per mole. Remember that usually reactions with a positive enthalpy change are not feasible, usually, okay? Minus tension, it's 800 degrees Celsius. So that's basically 800 plus 273 Kelvin. And what's del S? It's plus 218. So that's 218 divided by 1000, right? So plus 733 minus 800 plus 273 into 218 by 1000. That's a minus 233.914. So 733 minus answer gives you a value of 499 plus 499.086. Okay, so yeah, that is our answer. So since del G is positive, it will actually, it's a minimum of 3 SF, by the way. You could give this answer, you'd get full marks. It's not that strict in paper in chemistry compared to physics. Zinc nitrate undergoes thermal decomposition when heated. The reaction is similar to the thermal decomposition of group 2 nitrates. So let's decompose zinc nitrate. You know the drill. You've been doing this from S. ZnNO32 breaks down to form ZnO plus the brown gas nitrogen dioxide plus oxygen. And you know the ratio, it's 2:2:4:1. Have this memorized, please. 2:2:4:1. 2:2:4:1. Okay. It should be balanced. Next, the radii of some group 2 cations and Zn2 plus are shown in table 1.2. State and explain the trend in thermal stability of the group 2 nitrates down the group. You guys know something, that the thermal stability of group 2 nitrates and carbonates actually increases down the group. This is mainly due to the decrease in charge density. So according to Fajan's rule, there will be less polarization of the anion cloud, so it will retain more ionic characteristics rather than covalent characteristics, which results in a higher temperature for decomposition. So let's state the change. So thermal stability, there is an increase in thermal stability down the group. So we got 1 mark for that. No, we don't actually get 1 for this. We have to write the other point as well, that cationic radius or ion size increases down the group. Ion size increases down the group. Okay, so you could say that charge density of cation decreases down the group. That's also accepted in the marks scheme. So this overall is 1 point, and the second point is that there is less polarization of the anion. So there is less polarization, or less distortion of anion, or you could literally talk about the nitrate of the nitrate ion, NO3 minus, or you could say that there's less weakening. There is less weakening of the NO bond. This isn't present in every mark scheme, so I'd rather not write that. Okay, so just write there's less polarization of the anion. Use table 1.2 to suggest which group 2 nitrates are less thermally stable than zinc nitrate. Okay, so zinc has a radius, an ionic radius of 74 picometers basically. So I just told you that as you go down the group, ionic radii increases, so charge density decreases and there is less polarization. So clearly, as you can see, strontium and barium and also calcium. These three have higher ionic radii than zinc. Okay, so if we form a hierarchy, magnesium is over here, followed by zinc, then we have calcium, strontium, and barium. So these three are at a higher ionic radius, higher radii. As a result, they have less charge density, so they will polarize the anion less. However, on the other hand, magnesium has lower ionic radius, so it actually has higher charge density, so it will polarize the anion more. So magnesium is less thermally stable, right? That's the only answer. It's only magnesium nitrate. Could I clarify? But the others have higher ionic radii, which is why they are more thermally stable. Okay, moving on to question number 2. Hypophosphorous acid is an inorganic acid. The conjugate base of hypophosphorous acid is shown. So to make hypophosphorous acid from this conjugate base, you just need to add one more H. That's it. The difference between this and its acid form is an H only. So it should be H3PO2. This is hypophosphorous acid. If you add an H to the conjugate base, you end up with the acid. H2PO2 minus is a strong reducing agent. It can be used to reduce metal cations without the need for electrolysis. Equation 1 is shown. In an experiment, an alkaline HPO32 minus and H2PO2 minus half cell is constructed with concentration of H2PO2 minus 0.050. This is not standard conditions, because you know that the standard condition is 1 mole per dm cube, right? All other ions are at the standard concentration, so 1 mole per dm cube. Rate how the value of E of this half cell differs from the standard value. Okay, so you know that according to the Nernst equation, the new E value is equal to the standard E value plus. So if you look at the Nernst equation, it actually varies. Okay, it actually varies in our particular syllabus. They use a different form actually. They use a different form. It's actually RT by NF, but Cambridge just goes with 0.059 divided by N, right? 0.059 divided by N. That's what they use. Where N is the number of electrons transferred. Okay, so you don't actually need to memorize the value. It will always be given the equation basically. What you need to do is basically, wait, let me show you. Yeah, so we just go for E is equal to E standard plus 0.059 divided by N. Oxidized state by reduced state. Concentration of oxidized state by reduced state. So what is the oxidized state over here? If you guys think about it, it's always the one that comes first, honestly. Like check this, Fe3 plus Fe2 plus electrode. It's like this because if you go from left to right, it shows a reduction. So check this. Here oxygen has a charge of -4, hydrogen has a charge of +2. So to make a charge of -1, this needs to have a charge of, how much is it actually? +1, right? On the other hand, on the left hand side, if this is -2, hydrogen is +1. To get a charge of -2, what does P need to take? +3, right? Because +3 plus 1 is 4 and -6 is -2. And on the right hand side, it's +2 plus 1 plus 3 minus 4, that's -1 basically. All right, so the oxidized state over here is actually E is equal to E standard plus 0.059, the number of electrons transferred. Oh, we could just see this equation over here, right? I'm so stupid. This is the oxidized state. It gained electrons to turn into this, the reduced state. Here, phosphorus has a charge of +3. Here, it turns into +1 after accepting 2 electrons. So N should actually be 2. So we write it like this: HPO3 2 minus divided by concentration of H2PO2 minus. So if you actually do the math, we are going to get a value of E is equal to minus 1.57 plus 0.059 divided by 2. H2PO2 minus, the reduced state, actually turns into 0.050, and the oxidized state will remain normal at 1 since we bring about no change. So remember guys, there are 4 scenarios. If you increase the numerator, it becomes more positive. If you decrease the numerator, it becomes more negative. If you increase the denominator, it becomes more negative. If you decrease the denominator, it becomes more positive. So here we have decreased the denominator compared to normal. And if you do the math in the calculator, let's do this: 0.059 by 2 into 1 divided by 0.050. Okay, so that's minus 1.57 plus 0.59. This gives you a value of minus 0.98. See, you've decreased the denominator and you end up with a more positive E value. Okay, so that's the gist. There are 4 possible scenarios. So let's do this. All other answer. So rate how the E of this half cell differs. Okay, so it's going to be more positive or less negative. So the electrode potential E would become more positive or less negative. Okay, as I've shown on the right hand side. So they never, like, they do allow explanations using the Nernst equation, but recently I've seen that they've been using equilibrium. Okay, in what sense? Check this out. You've decreased the concentration of this, right? As a result, the equilibrium will shift to the right hand side. Okay, as you've increased the product, the equilibrium shifts to the right hand side. So what has happened? There is a tendency for the HPO3 2 minus to become reduced. There is a higher tendency for that species to be reduced. As a result, we know that this value, the half cell electrode value, actually refers to the reduction potential. So since it moved to the right, the equilibrium moved to the right, there is higher chance for reduction. As a result, the reduction potential will actually increase to a more positive value. That is the logic if you use equilibrium. Okay, so the logic is lower H2PO2 minus shifts equilibrium to the right hand side. Okay, as a result, it becomes a more positive value. And I've shown you the Nernst equation, so that's fine. The Cr3 plus Cr half cell has a standard electrode potential. An electrochemical cell consists of an alkaline HPO3 2 minus H2PO2 half cell and a Cr3 plus Cr half cell. Calculate the standard cell potential. Okay, so we don't need to deal with this value. We are just going to deal with our standard value. Okay, so check this. So this has a reduction potential of minus 1.57, and the chromium half cell has a reduction potential of minus 0.74. So the one which is more positive will get reduced preferentially. The one with the more positive electrode value will get reduced preferentially. As a result, chromium will actually get reduced. So let's find E cell. So chromium will get reduced. So I'm going to take its reduction potential, and I have to take the oxidation potential of the HPO3 2 minus H2PO2 minus half cell. Okay. So since the reduction potential is minus 1.57, the oxidation potential will actually be plus 1.57. So we end up with a value of plus 0.83 volts, which is feasible. Fine. complete the diagram to show how the standard electrode potential of the chromium half cell can be measured relative to that of the standard hydrogen electrode. Fine. So what do we need in the middle? We actually need a galvanometer or voltmeter, because this one on the left hand side, you know that there are three types of half cells: gas half cell, metal ion half cell, yeah, and metal ion in two different oxidation states. So for the gas half cell, you need an entry point for the gas and a platinum electrode. For an ion in two different oxidation states, you also need platinum electrode. But for the metal half cell, like the one here, you need the metal itself. Okay, so here hydrogen gas is entering, H2 gas is entering at 1 atmospheric pressure, and on this side we actually have the chromium electrode. So if you draw the beaker, it's something like this. It has to be immersed in the water, by the way, like this. And yeah, we have to continue drawing the salt bridge. The salt bridge will have to go down to the solution to actually complete the circuit. Okay, so let's label things. This is our voltmeter. This is the salt bridge. This is the chromium solid electrode. This is 1 mole per dm cube of chromium solution. Okay, since it's standard conditions, and we have to label the electrode here. I told you that it's going to be platinum, and the solution is going to be 1 mole per dm cube of H plus solution. You could give HCl, that's fine, but it's best if you just mention H plus. Okay, is that fine? That's all. Cr3 plus, yeah. Label 2.1 to show which is the positive electrode and the direction of electron flow in the external circuit. Fine. So guys, we have to identify the cathode first. This has an electrode potential of 0 volts, and the one on the right has an electrode potential of minus 0.74. So which one is more positive? Clearly the hydrogen electrode. So hydrogen or H plus will get reduced while chromium will get oxidized. Okay, H plus will get reduced since it has a more positive reduction potential. So this is clearly, since it is more positive, this is the cathode and this is the anode. So in an electrochemical cell, remember that the cathode is actually positive and the anode is actually negative. This side is actually negative. So the platinum electrode will actually be the positive electrode. So we need to label this platinum electrode. We can say that this is the positive electrode, or you could label it separately, right? And the direction of electron flow, remember that electrons will always go towards the positive electrode, so the electron flow should be in this direction, away from the chromium electrode towards the positive electrode, the standard hydrogen electrode, anti-clockwise. Okay, H2PO2 minus reduces Ni2 plus to nickel in alkaline conditions. Use equation 1 to construct the ionic equation for this reaction. Okay, so basically what happens, nickel is reduced to form, so nickel 2 plus is reduced to form nickel solid in alkaline conditions. So this will clearly be oxidized. So let's write down the equation. H2PO2 minus plus 3OH. This is oxidized to form 2H2O plus HPO3 2 minus. So we can get rid of these electrons. It's balanced. So on the left hand side, what do we end up with? We have H2PO2 minus. We have 3OH minus. We have Ni2 plus equals, and on the right hand side we have nickel, 2H2O and HPO3 2 minus. That's all. It's basically like after cutting it, I just wrote these down below here. Okay, see if that makes sense, guys. This is how you deal with it. Just get rid of the electrons, alright? The rest will just balance for you. Now H2PO2 minus aqueous actually reacts with hydroxide as well. Table 2.1 shows the results of a series of experiments used to investigate the rate of this reaction. The volume of hydrogen was measured under room conditions. Use the molar volume of gas and the data from experiment 1 to calculate the rate of reaction in mole per dm cube per second. Fine. How big is this question, by the way? It's pretty big. Alright, so as you can see, volume of hydrogen gas produced in 60 seconds is 6.4 cm cube in experiment 1. So they told us to use this specific value. We know that 1 mole actually occupies a 24 dm cube. We actually know that. It's in the table at the end. It's over here if you guys want to see it. Here you go. It's 24 dm cube at room temperature, not STP. Okay, so we can actually find out the number of moles from cm cube, and that occurred in 60 seconds, by the way. So let's do that. So the rate of reaction is equal to 6.4 divided by 24,000. So that's moles. We just converted to moles, and this occurred in 60 seconds time. So this divided by 60. What's the value? 6.4 divided by 24,000 divided by 60 gives you a value of 4.44 into 10 to the power minus 6. Fine. So if you see the value of Vm over here, it's actually 24 dm cube per mole. Okay, so when you divided, right, when you divided 6.4 cm cube by 24,000 cm cube per mole, we get rid of the cm cube and the mole actually went to the top, right? So we end up with 4.44 into 10 power minus 6 moles per second. And since these are given to mole per dm cube in the first place, the unit of rate of reaction is also found in mole per dm cube per second. Okay, but the unit here was actually mole and the unit here was second, so it's actually mole per second, right? But since the whole vessel, right, the concentrations are given to mole per dm cube, so we can say that it's given to mole per dm cube as well, mole per dm cube per second. Okay, we don't need to get into the details. Okay, you guys don't need that. The rate equation was found to be rate is equal to k H2PO2 minus to the power 1 and OH minus square. Show that the data in table 2.1 is consistent with the rate equation. Fine. So as you can see, when we doubled this, the rate also doubled over here, right? So clearly it's first order. So let's say that using experiment 1 and 2 as H2PO2 minus doubles, or this times 2 from experiment 1 and 2, what happens? Causes volume of hydrogen produced to double as well, or times 2. So first order with respect to H2PO2 minus. Okay, that's fine. Next, let's go to the second one. This is one of them. What about the other one? We want to prove OH is second order. So what happened to OH exactly? We can use 1 and 3, yeah? So H2PO2 is actually triple the value. So we would be expecting this, which is 6.4 into 3, which is 19.2. However, we're actually getting 4.8. Why? Because OH was halved. So if you do the ratio, 4.8 divided by 19.2, how much is it? 4.8 by 19.2 is actually 1 by 4. And that is consistent with, check this, it is consistent with 1 divided by 2 whole square, which is also 1 by 4, which indicates that OH minus is second order. Okay, so let's write this down. In experiments 1 and 3, what happened? H2PO2 minus actually trebles, and OH minus actually halves from experiment 1 to 3. So the volume of H2 falls, right? To how much exactly? Check the total one, 4.8 by 6.4. That is actually 3/4 of the original. 3 times due to this, and 1/4 due to this one, half square. So falls to 3/4 of the original. Okay, so if it is first order with respect to H2PO2, then it must be second order with respect to OH minus. But they didn't really explain it in a good way in the mark scheme. Okay, but hopefully you understood my explanation, alright? You could write that down here as well. This last point was optional, by the way. So basically you could write like this, like due to the value being triple or trebled of H2PO2, the value increased by 3 times. However, since OH minus halved, if it is second order with respect to OH minus, half square is 1 by 4, right? As a result, it becomes 3/4 of its original value. That's the logic behind this, alright? So the units of the rate constant K. So we know that a rate is mole per dm cube per second, and here we have mole per dm cube square times mole per dm cube. As a result, we end up with K is equal to mole minus 2 dm plus 6 second minus 1. So mole minus 2 dm plus 6 second minus 1. Okay. The experiment is repeated using a large excess of OH minus. Okay. So the reasoning for doing this is actually to make the concentration of OH minus virtually constant. It's not changing anymore. So rate only depends on the concentration of H2PO2 minus, because OH minus is virtually constant. Find out the half-life. So this technically turned into a pseudo first order reaction, since OH minus is basically constant. Now you guys know for a first order reaction, the formula for half-life is ln 2 by K. So here T half is equal to ln 2, or 0.693, divided by K1, which is 8.25 into 10 to the power minus 5. So 0.693 divided by 8.25 into 10 to the power minus 5, which gives you a value of 8,400 seconds. Fine. Describe how an increase in temperature affects the value of the rate constant K. So you guys know that rate is proportional to temperature, right? So as temperature increases, rate also increases. Okay? And given that the concentration remains the same, the value of K, the constant, must also increase. So just remember this, as temperature increases, rate constant also increases, mainly due to more effective collisions, more K. K1 increases with temperature. Fine. Students suggest that the reaction between H2PO2- and OH2- might happen more quickly in the presence of a heterogeneous catalyst. Describe the mode of action of a heterogeneous catalyst. It mainly works by, adsorption, hydrogen and nickel in hydrogenation of alkenes. So let's do this. The first point is reactants adsorb to surface of catalyst. What does adsorb mean? Basically sticking to the surface by intermolecular forces. It does not penetrate into the bulk of the substance. So, for example, nitrogen and hydrogen, they actually form new bonds with the solid over here. As a result, the bonds between them weaken. So, bonds in reactant weaken. All right. So, what happens afterwards? The reaction occurs, products are made, right? And the products finally, what do? They are opposite of adsorbed, desorbed, and they are desorbed. Okay, that's that. They mentioned something in the mark scheme. They said ignore bonds are broken because bonds are broken. This happens in all reactions. So you need to specifically say that bonds weaken. Okay, that's the thing that you need to mention. And instead of products are desorbed, you can say that products are deabsorbed or released or diffuse away. Same thing. Okay, products are desorbed or diffuse away. That's also fine. Okay, moving on to question number 3. Transition element. I was talking about this sometime back. So how many questions do we have? 6 in total. Okay, we're doing question number 3 right now. Define transition element. A transition element is a D block element which forms one or more stable ions or compounds or oxidation states. I just told you a bit before, with incomplete or partially filled d orbitals. Or d shells or d subshells. All right. Vanadium shows typical chemical properties of transition elements, including variable oxidation states. State 2 other typical chemical properties of transition elements. Okay, not physical properties, chemical properties. Firstly, they behave as catalysts. They form colored compounds. And last but not least, they form complex ions. Okay, you guys need to memorize this thoroughly. Now, explain why transition elements have variable oxidation states. This is a very important question because it's repetitive. Basically, remember the 4s orbital and 3d orbital, they basically have really close energy levels, so they kind of overlap. So the D and S subshells or orbitals are close or similar in energy. Okay, there was an alternate answer available. The maximum tool to allow this. You could say that the electrons in D and S subshells or orbitals are available for bonding. This is true in a sense, Okay, this is true in a sense. Like in the other elements, you don't have access to the d electrons. Okay, but here you do. VO2 plus can be reduced to V2 plus by C2O4 minus in acidic conditions. The ethane dioic acid, the ethane diode ion basically. So this is the reaction in titration. 25 cm cube of 0.03 mol per dm cube VO2 plus aqueous is added to 10 cm cube of dilute sulfuric acid. Fine. Acid basically acts as a catalyst. A solution of 0.04 mol per dm cube ethane diode is then added from the burette until the endpoint is reached. The titration is repeated and concordant results are obtained. Concordant, what does this mean? This is important for paper 5. Results which are within 0.10 cm cube of each other. Show that these results are consistent with the stoichiometry of equation 2. Alright, let's do this. So, let's find out the moles of vanadium. So, sorry, moles of, VO2 plus, my bad. Concentration times volume, dm cube. This gives you a value of 0.25 by 1k times 0.03 gives you a value of 7.5 into 10 to the power minus 4. Now, according to the molar ratio, ethane diode should have 1.5 times the number of moles, right? Okay. That's one way of doing it. Ethane diode should have the like you have to multiply half because vanadium VO2 plus is 2 times and then multiplied by 3 essentially 3 by 2 times. So many methods exist to prove this actually. They even wrote this in the mark scheme. For example, I'm going to show you one followed by the one in the mark scheme. I know that the moles of C2O4 2 minus should be 7.5 into 10 power minus 4 by 2 times 3. So how much is that? By 2 times 3. 1.125 into 10 power minus 3 mole. Now, we know the concentration, right? So can we not find out the volume? We know that moles equals to concentration into volume. So volume equals to moles by concentration. So volume of ethane diode is equal to moles by concentration 0.0400, which is 0.028125 dm cube, or times 1000, 28.125 cm cube, which is the average of those two values. Yeah, you can show that 28.15 plus 28.10 divided by 2 is 28.125. I would do it in my exam this way. Now, what they showed in the mark scheme is alternate approach. They showed this step followed by the moles of ethane diode. They actually found it out using these values. Half of 28.15 plus 28.10 by 1000 times n C2O4 2 minus is equal to times 0.0400. Gives you a value of 1.125 times 10 power minus 3. Now, if you do the ratio, right, of VO2 plus is to C2O4 2 minus, you get a value of 7.5 into 10 power minus 4 is to 1.125 into 10 power minus 3. So if you do that, you're going to get a value of 1 is to 1.5 or 1 is to 3 by 2. That's approach number 2. These are alternate approaches, okay? Both are fine though. Now, an excess of ethane diode reacts with VO2 plus to form a mixture of two octahedral complex ions. The complex ions are stereoisomers of each other. Ethane diode is actually a bidentate ligand. Each complex ion contains a V2 plus cation and 3 C2O4 2 minus ions. Complete the diagram to show the three-dimensional structure of one of the complex ions. So they actually form optical isomers. So in total we have 1 2 plus and 3 2 minus. So what do we get? 2 plus 2 minus 6, which is minus 4. That's the net charge. Okay, so if we draw it behind, it's like this. In front, it's like this. So we have to draw it like using this, right? So one of the isomers is like this. Okay, this is one. You don't have to draw it this way. There were multiple options. Okay, like you could even draw it like this. Okay, guys, wait, let me show you. This was also fine. It's just a convention that the first one that we draw is like this. Okay, and the optical isomer is going to be its mirror image, right? So this is the one of the optical isomers. Now V2 plus can be oxidized by H2O2. Identify the vanadium species that forms when excess of H2O2 reacts with V2 plus under standard conditions. Explain your answer with reference to data in table 3.2. This is a really good question. Do you know why? Because it's a repeat. I actually really like this question. There was a question like this back in 2016. Okay, I want to show you guys the variant actually. We got this back in 2016. I just need to find it. Give me 1 sec, okay? Just give me 1 sec. So this is a question from ON1641, question number 4. ON1641, question number 4. Wait. This one. Okay, almost the same question, like similar but not the same. Basically, there we had, vanadium reacting with iron, but it followed the same principle. You guys can check this out if you want. This is the ON1641, question number 4. Check this out after you solve this paper. So essentially, the reaction will keep on occurring until E cell is pulsed. Yeah, until E cell becomes negative. Okay, till then it keeps on occurring. So let's take a look at the first one. V2 plus getting oxidized. So what's the oxidation potential of V2 plus getting oxidized? It's plus 0.26, and H2O2 being reduced is plus 1.77. So if you add it up, plus 1.77 plus 0.26 gives you a value of 2.03, which is feasible. Okay, so we got V3 plus. We have access to this now. Now let's try checking the next one. Okay, now V3 plus getting oxidized to VO2 plus. VO2 plus. So that has a reduction potential of plus 0.34. So the oxidation potential will be minus 0.34, and we're still going to take plus 1.77. So plus 1.77 minus 0.34 gives you a value of 1.43. Great, it's still positive, so it's still feasible. So we just ended up with VO2 plus. Now let's see the last reaction. Now VO2 plus. Let's see if it gets oxidized to VO2 plus. Let's see. So the reaction potential needs to be minus 1.00. Okay. So it's 1.77 minus 1. That gives you a positive value of plus 0.77. So it's still feasible. Okay. So it's like you do not consider plus 1.77 once. You actually consider it thrice. One time with this, the second time with this, and the 3 times with this. As long as it's positive, it's going to be feasible. By the way, I missed something. Sorry, I actually missed the charge over here. You have to show the charge, and I also missed this over here. Really sorry about this. So it has a net charge of 4 minus. I just showed you how. Okay, so back to this. So the final product that we'll be getting is in fact this one over here, because all three reactions were feasible. So we are going to write VO2 plus, and the logic being, the reasoning is, this is because, you know, the standard electrode potential of H2O2 is positive. Check that it's positive than all three of these, right? H2O2 is largest or the most positive, anything works. Concentrated acidified H2O2 can react with V2 plus to form VO3 plus ions. VO2 3 plus contains vanadium combined with peroxide, with the peroxide anion. This is the oxidation state of vanadium in VO2 3 plus. So this is basically vanadium combined with peroxide. So you guys know of hydrogen peroxide, right? H2O2. So here oxygen is special because each oxygen actually has an oxidation number of -1. As a result, two oxygen atoms have an oxidation number of -2 in total. So each hydrogen has an oxidation number of +1. So here, check this out. In VO2 3 plus, these two oxygens together have an oxidation number of -2, -1, -1, -2. And vanadium we can consider to be x. So can we write that x minus 2 is equal to +3? So x is equal to +5 actually. So the answer should be +5. Clear? Great. Moving on to question number 4. Finally, we're doing an organic question. So we have 3 questions left, 4, 5, and 6. These two compounds are synthesized by different methods. Several methods can be used to form ethylamine. Ethylamine forms when ethanamide. What is this? CH3CONH2. When it is reduced to form, CH3, CH2, and H2. You guys know that if you reduce an amide, you actually get an amine, right? Using LiLH4. Write the equation for this reaction. Use nascent hydrogen to represent one atom of hydrogen from the reducing agent. Okay. So let's do this. CH3CONH2 along with some nascent hydrogen gives you CH3CH2NH2. Now you got to do something with the oxygen, right? If you ever have extra oxygen in oxidation or reduction reactions, please just convert them to water. Okay, that's the trick. So the extra oxygen will go as water, H2O. And let's try to balance this. How many hydrogens do I need? I added 2 hydrogens here and 2 hydrogens here. So in total, I need 4H. Ethylamine is a production of bromoethane with ammonia. Check this. Bromoethane, CH3CH2Br plus NH3 alcoholic. This actually gives you CH3CH2NH2 plus HBr. Yeah. So what are the conditions and what is the mechanism? The mechanism is actually nucleophilic substitution. This is actually AS chemistry. And the conditions, I just told you, you need ethanol dipped in, ammonia dipped in ethanol, and it has to be heated in a sealed tube. Ethanol, and it has to be heated in a sealed tube or heat under pressure. So heat under pressure or heat in a sealed tube. Fine, I prefer heat in a sealed tube, really important. The reaction in A2 is also from secondary and tertiary amines. So this is the identity of a secondary tertiary amine formed in this reaction. What does this mean exactly? You guys need to understand that. Who was the nucleophile in part 1? NH3. But in part 2, this can also act as a nucleophile. The products, there can be a chain reaction like free radical substitution. Basically, this thing over here can act as a nucleophile again and react with CH3CH2Br. It can react again with CH3CH2NH2. Okay, so here NH3 was acting as the nucleophile, but now this guy over here is acting as the new nucleophile. So check this, what's going to happen? Basically, what happens in one reaction, NH3 basically lost one hydrogen, and the remaining part NH2 was attached to CH3CH2 in the place of Br. So the same thing will happen here essentially. It's just that this NH2 will lose one hydrogen. So what do we end up with? We basically get CH3CH2. Here we get the N, but this N will have another CH2CH3 attached to it, and we have one H remaining, and it's going to release HBr again. However, now in this step, this one will act as the nucleophile in part C again. Okay, it's chain reaction which keeps on occurring until the amine compound has no more hydrogen remaining. Okay, so CH3CH2Br will react with this compound again, CH3CH2NCH2CH3H. It is acting as the nucleophile. What will you get? CH3CH2, N comes in the position, CH2CH3, and here we get CH2CH3. We don't have any H remaining, so this is the end point. Okay, so how can you write this in a short form? You can write this as CH3CH2 2NH, and here you can actually write this as CH3CH2 3N. I think that should be fine. So yeah, those are the possible products. So it's identity of a secondary or tertiary amine. It's going to be CH3CH2 twice NH, or the alternate one was, tertiary one was CH3CH2 3N. I actually explained this in my A2 organic chemistry video, A-level organic chemistry advanced level video. I'm going to link that up top if you guys want to see that. It's a great video, by the way. Shameless plug. Moving on, ethylamine is a weak base. Compare the basicities of ethylamine. Okay, ethylamine, it's the best base over here, followed by ammonia, and the worst one, phenylamine aniline. Why though? Basically, the basicity of a base actually depends on the availability of its lone pair. Yeah, so ethylamine is the most basic because of the positive inductive effect of the ethyl group. It actually makes the lone pair more available. Okay, so ethylamine is the most basic, followed by ammonia, and the least basic is actually phenylamine. Okay, let's answer. So let's talk about the good points about ethylamine, right? So for ethylamine, the alkyl or ethyl group is actually electron donating, or has positive inductive effect, group with positive inductive effect. That's literally what they wrote in the mark scheme, and this actually increases the electron, this increases the electron density on nitrogen. Okay, so that's what happened as a result. It is a stronger alkali. Why? We need to mention that mainly because you need to link it with any of the points. Basically, the order of basicity is based on the ability is based on the ability of base to gain or bond with or accept a proton or donate its lone pair to a proton, basically. So who is the best at doing that? Ethylamine. So lone pair is more available. I made this up. It's not in the mark scheme, but you can write it. What about the last point? What about phenylamine? Why is it so bad? Basically, for phenylamine, you guys know that there's a benzene ring, right? So the lone pair or the p orbital from nitrogen in NH2 is actually the electron is the lone pair is delocalized, or the p orbitals basically the p orbital basically overlaps with the pi ring or benzene ring, and this basically decreases the electron density of or on nitrogen. Yeah, so the lone pair is less available. Okay, hopefully you guys understood. This is a common question, and ammonia is in the middle. Pure phenylamine can be prepared from benzene in 2 steps. Draw the structure of the intermediate compounds. Suggest reagents and conditions for each step. You can never produce it directly. This is the process. You end up with benzene. Check this. Followed by nitration of the benzene ring. Followed by reduction of nitrobenzene to get aniline. So what is our intermediate? This guy over here, yeah? We need to draw that. Fine. So what's the condition for step 1? Basically, it's concentrated nitric acid and concentrated H2SO4, and the temperature is at 25 to 60 degrees Celsius, anything in between this range. Okay, you can write 55 degrees Celsius. And what about step 2 reduction? We basically use tin with concentrated HCl. Reduction with tin and concentrated HCl plus heat. Okay, remember these, never forget. You'll always face this in your exam. So you can make nitrobenzene in 1 step, but aniline requires at least 2 steps. What about phenol? It requires more steps. Basically, you need to convert aniline to a diazonium salt, and then you need to hydrolyze it with H2O at room temp. Okay. Figure 4.2 shows some reactions of phenylamine. So phenylamine reacts with aqueous bromine to form a white precipitate at room temperature, just like phenol. It forms 2,4,6 tribromophenylamine. So draw the structure of W. Basically, W is this. Br, Br, Br 2,4,6. Okay. It occurs at room temperature. This is characteristic for aniline and phenol. 2,4,6. 2. Fine. Next, state the reagents used in reaction 2. So what's reaction 2? We convert it to a diazonium salt. So we actually use nitrous acid. Okay, HNO2. We use nitrous acid, HNO2. And the temperature has to be, below 10 degrees. That's what they wrote in the syllabus actually. Let me show you. Let me show you the syllabus. Wait. HNO2 or NO2 but diacid below 10 degrees Celsius. Okay, that's the temperature. And another temperature is for nitration. Basically, the temperature has to be, where is it? 25 to 60 degrees. That's it. So the reagents used are either HNO2 directly, or you can go for NaNO2 plus a dilute acid. So dilute acid includes something like, maybe HCl, aqueous. Okay, any dilute acid works actually, or you could just say H plus aqueous. That also works. Basically, the aqueous makes it dilute. Okay, is that fine? I just go for HN2, and if they wanted the condition, it would be less than 10 degrees Celsius. So maybe 5 degrees Celsius. Benzodiazepam chloride, C6H5N2Cl, and X react together to form an azo dye. So we can actually get the azo dye from here. So look here, we had this compound. This is our benzene diazonium chloride, and on the other hand, on this side we just had phenol. Yeah, so always remember the bond actually forms in carbon number 4 opposite to phenol, and this nitrogen over here, they just form the bond to form this compound over here. So clearly compound X was phenol, but phenol has to be activated. Okay, so we're going to say that it was phenol. But what is the necessary condition for the reaction to occur? It has to be activated by dissolving in an alkali like NaOH or KOH. Okay, it has to be dissolved in an alkali for the reaction to occur. Suggest a use for Y. Where is Y or this dye used? Essentially, it's basically used in textile. Okay, textile for dyeing. Okay, so it's used in dye stuffs. That's what they wrote. In garments and textile. Next, we go to E. What is a monodentate ligand? So it's basically a species which contains a single lone pair of electrons. Okay, so it's a species that contains a or one lone pair of electrons that forms a dative covalent bond to a central metal atom or ion. Is that fine? Pretty common answer. Cu2 plus aqueous reacts with ethylamine to form CuCH3H2 H2O4. There are three-dimensional structures to show the two geometrical isomers. So basically we have six monodentate ligands, out of which 4 are the same or they're similar in a ratio of 4:2. So here the combination that we get is cis-trans. The trans isomer will have the two unique ones in one straight line, and the cis one will just have those two that are not in a straight line. That's how it works. Okay, so for the trans isomer you need to allocate them in one straight line. Okay, so let me show you how. I usually do it like this over here. So the N is attached over here, and here the N is attached. Okay, and we have CH3 over here. We have CH3. So our job here is done essentially because it's in one straight line. And what else do we need to do? Check this, just like the previous one. 1, 2, 3, 4. Here you go. So here, you need to show that it's connected to the oxygen, by the way, or else you won't get marks. OH2, 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 OH2. So this is the transition on the left, and on the right hand side it's almost the same diagram. It's just that you can't have them in a straight line. Okay, so for example, what you can do is, check this, we can write OH2, OH2, and I can just move this away from here. I can write OH2, You can put this over here, OH2, and you can put NH2 CH3 over here. It doesn't have to be here. It could also be here or here or here. It would still give you the cis isomer basically. Okay. So this is one way of drawing it. In the mark scheme, they have drawn it in a different way, but that's totally fine. You don't have to draw it like that. Like this way is completely okay. The other ways, they've recently started this. I've seen a variation in Feb March 2022 as well. I'll show you guys that in a bit. So the other variation is this, where you draw these four ones in one single plane. You draw four atoms in one single plane like this, OH2, OH2, and you draw one coming out of the plane and one going into the plane like this. See, the one coming out of the plane and one going into the plane. Okay, so here for the cis isomer, the OH2s are gonna be here. Okay, and for this one, like if I draw OH2 here, I need to draw the ethylamine component over here. So it's NH2CH3 over here. Okay, NH2CH3, or this is how they drew it. CH3, same thing guys, it doesn't really matter. So I wanted to show you an example where I got this. Like they didn't used to draw this before 2022. Like the first time I saw it was back in 2022, March of 2022 actually. Here, let me show you. March 5, 2022, question 4. Look, they drew this compound in this way over here. Okay, so it's fine, like anything works. But since they gave the diagram like this, you had to go along with it. But here you have complete independence. Like you didn't have to draw it the way that's shown in the mark scheme. You could also draw it how I showed you the beginning. Okay, I would highly recommend watching this video as well if you're unclear with it. I've solved Markship 22 as well. So there you go. So basically remember, the trans isomer does not have a dipole moment because it cancels out as they are along a straight line. However, in this compound there is a dipole moment. Yeah, state the coordination number of copper. So since it has 6 dative covalent bonds, so the coordination number will also be 6. The coordination number depends on the number of dative covalent bonds. Okay, so CD2 plus ions form tetrahedral complexes with CH3 and H2, OH minus and Cl minus ions, as shown in equilibrium 1, 2, and 3. Give the units of K step for equilibrium 1. So basically, it's mole per dm cube above, and below it's mole per dm cube times mole per dm cube to the power 4. So we can get rid of these, and we actually end up with mole minus 4 dm16. Yeah, sorry, 3 fourths 12, my bad, dm12. So that's mole minus 4 dm12. Let's go. Write an expression for K step for equilibrium 3. Okay, let's do this. So it's CdCl for 2 minus divided by CD2 plus times Cl minus to the power 4, like this. And the charge needs to be inside, and you should definitely mention the state symbols. They've been doing that recently, so you need to mention that equals, okay? And the power should be outside the third bracket and the charge should be inside. Could I clarify? The solution of Cl minus aqueous is added to CD2 plus and allowed to reach equilibrium. The equilibrium concentrations are given. Use your expression in F2 to calculate the concentration of CdCl for 2 minus, okay? So K step is 6.3 into 10 power 2. 6.3 into 10 to the power 2 is equal to CD Cl4 2 minus divided by CD2 plus is 0.043 times 0.072 to the power 4. So let's do that. It's going to be equal to CdCl4 2 minus is going to be equal to 6.3 into 10 power 2 times 0.043 times 0.072 to the power 4. 0.072 to the power 4 times 0.043 times 6.3 into 10 to the power 2. That gives you a value of 7.28 into 10 to the power minus 4. Okay. In chem, I just told you that there's no problem with SF. You can write 2. A minimum of 2 is fine. By the way, guys, if you do like the content, please like the video and subscribe to the channel. It helps a lot. When CH3 and H2 is added to CD2 plus, a mixture of a basically a tetrahedral or square planar complex and CdOH4 2 minus forms. Suggest how the CdOH4 2 minus aqueous ion is formed. So basically, guys, uh, it's kind of like a ligand exchange reaction. But how though? Like we know where CH3 methylamine CH3NH2 is coming from. We have added that aqueous solution, but remember the aqueous solution also contains water, and water dissociates to form H plus and OH minus. OH minus actually has a lone pair, so it acts as a ligand which can displace the methylamine ligand. Okay, that's how it happens. Understood? This is a huge question, by the way. So also OH minus is produced because it's a base, right? So when you add it to water, methylamine, it actually accepts protons from the water, so some extra OH minus ions are produced. Okay, so let's write this down, that CH3NH2 is basic, so it reacts with water to produce OH minus, which ultimately forms a complex with CD2 plus aqueous. Fine. CD2 plus exists as a complex ion CdH2O6. Identify the most stable and the least stable of the complexes in tail for one, placing one tick in each column. Explain your answer. Okay, so let's check this. Check this table. So guys, the higher the value, the more stable it is. So this aqueous ion is the least stable because all of these values are higher. And which is the most stable? This CdOH42 minus, because it has the highest value, into 10 to the power 8. Followed by this methylamine complex, and lastly followed by CdCl4. And the weakest is CdH2O6. Okay, so CdH2O6 is essentially the least stable because everyone displaces it. Check it out. Everyone displaces it. All methylamine, hydroxide, and chloride. But hydroxide complex is the most stable because it has the greatest value, 5 into 10 power 8. There you go. Okay, so what's the answer? CdOH4 2 minus has highest K step, right? And an optional point was, and all K step values are given greater than 1. Why is this essential? Because if any of these values were less than 1, that would mean the one on the left was more stable. But since all of these are greater than 1, so CD2 plus is, if any of these values were less than 1, that would mean that CD2 plus equals the complex with water would be more stable than the ones on the right. But since it's positive, the one on the right is more stable. Okay, that's the concept. Okay, done with question number 4. We move on to the next one. It was 27 marks in total. That's huge. So we have two questions left. Question number 5 and 6. 5 is organic, and 6 basically deals with analysis and chromatography. So let's start with question number 5. Come on. Tiobuterol is used in some medicines. Tiobuterol contains a benzene ring in structure. Describe and explain the shape of benzene. In your answer include the bond angle between carbon atoms, the hybridization of the carbon atom, how orbital overlap forms sigma and pi bonds between the carbon atoms. Let's do this. You can draw a diagram, but let's answer through the text first. So firstly, the bond angle is 120 degree, and the shape is planar, or a hexagonal ring planar, or you could just say that it's trigonal planar, yeah, because they're sp2 hybridized. So all carbons are what? Carbons are sp2 hybridized. Fine. So what does the benzene contain? The benzene contains delocalized electrons in the pi bonds or pi system, basically. And they told us to mention how the orbitals overlap to form sigma and pi bonds. Let's do that. So the sp2 orbitals between CH and CC overlap end to end, right? Overlap to form sigma bonds. Basically, the sp2 orbital of carbon and s orbital of hydrogen, or the sp2 orbitals between both carbons. Also, p orbital from each carbon atom overlaps sideways with each other above and below the ring to form pi bonds. Okay, this is really important. So let's begin. We can draw the diagram if you guys want. This is our benzene ring. We can show that it's hexagonal, and we can also show the bond angle is 120 degree. You can draw the p orbitals like this. And you can show the orbital overlapping like this, basically, above and below the ring. You have to label it, okay? P orbitals overlap sideways above and below ring. Okay, is that fine? So there you go. Really important. In a synthesis of tiobuterol, this compound over here, what do we need? First, we need to halogenate the benzene ring. So show how Cl2 actually reacts with Cl3 to generate the electrophile. Fine. This is pretty straightforward. Cl2 reacts with AlCl3 to form Cl plus and AlCl4 minus. Okay, so we just generated the electrophile. Now let's show the mechanism. So what happens? At first, there will be attack by the electrophile on the nucleophile. So the electrophile here is Cl plus. Sorry, the electrophile here is Cl plus. The electrophile attacks the nucleophile, right? But remember, arrows always need to be drawn. How? From the nucleophile to the electrophile, okay? So the nucleophile actually the electrophile attacks the nucleophile, but we draw the arrow like this. What's the next step? Basically, we form the bond with chlorine, and we have to draw a semi-lunar structure which encompasses the 5 carbons except the one that was attacked. And now what happens? We basically end up with a heterolytic fusion of the bond, of the CH bond. And at the end, we get this final compound along with the byproduct H plus, which will combine with AlCl4 minus to form HCl, steaming fumes. Okay. In the second step of the synthesis, it actually involves the reaction of chlorobenzene with ClCO H2Cl, also in the presence of an AlCl3 catalyst from a compound Q. So this is actually Friedel-Crafts acylation, right? This is an acyl chloride. So we know that this section, right? This section over here will be attached to the benzene ring over here. Halogens are orthopara directing, or they direct towards the 2,4,6 carbon atoms. As a result, this is fine. This is totally okay. Name the mechanism. Fine. Let's name it. It's called Friedel-Crafts. The type of reaction is Friedel-Crafts acylation, but the mechanism is electrophilic substitution. Electrophilic substitution. Fine. Okay, so let's take a look at part 2. Draw the structure of an isomer of Q that forms as an organic byproduct of the reaction in step 2. So this is a bit complicated, but there are many ways in which you can answer this actually. The first one being, check this. Cl, or the halogen chlorine, is an orthopara directing group which reacts to 2, 4, 6 positions. So 2 and 6 are the same actually. So here Friedel-Crafts acylation has taken place. So basically we got rid of this chlorine. But guys, instead Friedel-Crafts alkylation could have taken place at the same carbon atom, yeah? So this is the compound that you'd be getting. Friedel-Crafts alkylation but with the same carbon atom, okay? So what do you guys get? After Friedel-Crafts alkylation, this is the compound. I'm just going to copy this. The benzene ring will be attached to this carbon over here. It's attached to that carbon, followed by copy paste of this part, this thing over here. So yeah, here you go. This is the one that formed, okay? Basically, because take a look at this. What if you had a benzene ring over here with chlorine, and you had something like, ethyl chloride, 1, 2 here, ethyl chloride. After Friedel-Crafts alkylation, you could get this compound, right? Check this. Here, after Friedel-Crafts alkylation. So I just added this compound over here, right? We got rid of this chlorine and this part was added. This part was added, yeah? So this is one way of doing it. What is the other way? Like, what if you made it go to the, instead of the ortho position, why don't you make it go to the para position like this? There are two options. So para, right? So you can make it go here like this. Friedel-Crafts acylation, okay? Friedel-Crafts acylation. 1, 2 chlorine like this, or the alternate of this is just Friedel-Crafts alkylation but on the 4th carbon, okay? Chlorine over here but Friedel-Crafts alkylation. So let's do this. So I drew this carbon over here, this one. Now I have to go through this part over here, okay? And what about the last one? They also accepted this in the mark scheme. Even though chlorine is not an isn't a meta directing group, but you could still draw the meta isomer. Okay, both, by the way, both meta isomers. You could either draw the one with, Friedel-Crafts acylation or Friedel-Crafts alkylation. Okay, so let's do this. Acylation first. So carbon number 3, Friedel-Crafts acylation, 1 over here and chlorine over here, or Friedel-Crafts alkylation. So how does alkylation go? We draw this hand over here, this first hand, followed by, the other part, the SL group over here. Okay, so let's go through a brief overview. Basically, we had a compound where Friedel-Crafts acylation occurred in the second carbon. So the first possible option is Friedel-Crafts alkylation on the second carbon. What are the other options? Friedel-Crafts acylation or alkylation on the fourth carbon, since chlorine is an para-directing group. Or you could also draw the minor product, which is the meta-directing product, Friedel-Crafts acylation or alkylation on the third carbon atom, which is very unlikely though. Tricky question. The reactants used in step 2 contain acyl chloride, alkyl chloride, and aryl chloride functional groups. State and explain the relative ease of hydrolysis of acyl, alkyl, and aryl. Guys, acyl chlorides are the easiest to hydrolyze. Meanwhile, on the other hand, aryl chlorides don't hydrolyze. Aryl chloride, okay, they don't hydrolyze at all. And alkyl chlorides fall in the middle. So what's the logic behind this? Let's try to explain. Basically, the acyl chloride, COCl, is attached to two electronegative atoms, right? So acyl chloride, the acyl chloride's carbon in CCl bond is more electron deficient since it is also attached to an oxygen atom. As a result, there is a very high positive interactive effect. Or you could word this as the CCl bond is weakest or weakened the most since it is also attached to an oxygen atom or two electronegative atoms. Fine. That's marking point number 1. What about marking point number 2? Why don't they undergo hydrolysis? Basically, aryl chlorides have no hydrolysis because the CCl bond is actually strengthened. Why? Because it is part of the delocalized system of the benzene ring. Okay. Or the CCl bond actually has a partial double bond characteristic. So CCl bond is stronger. Okay. Or you could say that the lone pair or p orbital actually delocalizes within the pi ring. Okay. Or you could say that the lone pair or p orbital on chlorine delocalizes with pi ring. So CCl bond is stronger. That's marking point 2. You had to write any 2. Okay, I'm gonna give you the last point. You had independence to write any 2. What about the last one though? For the last one, we are going to talk about the alkyl chloride. So the alkyl chloride CCl bond is actually strengthened, okay, by the positive inductive effect, by the electron donating effect or positive inductive effect of whom exactly? Of the alkyl or R group compared to acyl chlorides, of course. So basically it's stronger, yeah, compared to acyl chlorides. Or you could basically say that the carbon atom has smaller del plus. Or you could say that the carbon atom has smaller del plus and the CCl bond is stronger. Fine. Then the CCl bond in COCl, due to carbon being attached to only one electronegative atom, due to carbon being attached to only one electronegative atom. Oh god. Okay, so basically in COCl both of them pull, so this is really high del plus, but in CCl only this pulls, right? So it's del plus but not that high comparatively, okay? So any two works. Hopefully you guys get it. Really common question. Next, tolubutyl is produced from Q as shown. Guys, look what happened. Basically the ketone turned into a secondary alcohol, so we reduced it. The ketone is reduced to a secondary alcohol, and what happened to this chlorine over here? It was substituted by this ammonia compound, amine compound, sorry, basically this amine compound. This one actually took the position of chlorine. I was telling you guys that all amine compounds can act as nucleophiles given that they have hydrogens available, but at the end product, the last product is one hydrogen less. So let's begin. Draw the structure of Z in the box. So you have two options. For example, if I write step 3 as reduction, okay, if I write step 3 as reduction using, to reduce the ketone, I can use NaBH4 or LiLH4, okay, in dry ether. Then I have to draw the compound as this. Okay, and then what do we get at the end? We need to, add this compound. What is this basically? NH2C followed by CH3, CH3, CH3. So that's basically NH2C, CH3, 3. So CH3, 3, CNH2 in ethanol, of course. Heat in a seal tube. Heat in a seal tube is usually for ammonia only, though it's just heat. So this is one option. What is the alternate route? Like, what if you exchanged the order? Like, you could do CH3, 3, CNH2 before, in ethanol before, followed by NaBH4. Then the reduction would come later, and you would get this compound first. You would still get the ketone over here. The ketone would remain. However, instead of chlorine, you'd get this compound. Like this would be there first, right? So it's up to you guys which route you take. The synthesis produces two enantiomers of tolubutyl. Guys, enantiomers. Basically, this has been added from 2022 onwards. Enantiomers refers to the two pairs of optical isomers, right? So tolubutyral actually has a chiral carbon over here. This is chiral. So we actually get two enantiomers. But remember that during organic synthesis, not all enantiomers are useful. Like one might be useful while the other one might not be that useful. Understood? So what are enantiomers? Enantiomers are basically a pair of optical isomers which have same physical and chemical properties, but they have two different things. They might have different biological activity and rotate the plane of polarized light in opposite directions. Okay, so this is how you define it. Molecules that have identical physical and chemical properties, okay, but rotate the plane of polarized light. You learn Mal's law in Becknius, right? Plane of polarized light differently or in the opposite direction. Great question. So just one disadvantage of producing two enantiomers. Like one might be biologically useful, right? But the other might be useless, harmful, toxic. Reduced or different biological activity of the other enantiomer, the useless one. Or you could say that there might be lower yield of biologically active molecule. Or you could say that, need to separate the optical isomers to form the pure active isomer. Need to separate the optical isomers to form the pure active isomer, to form the pure active isomer. Okay, so write any of these three over here. So two enantiomers, like we don't have control, okay, but both enantiomers will be produced. However, recently there have been some chiral catalysts that we can use to form one enantiomer, one specific enantiomer. Okay, so that's what they asked. First time this question has arrived in the question paper, but this was mentioned in the syllabus. It was there. If you guys want to check, I can show you. Check this out, guys. So it's best if you go through the syllabus once at least. It gives you a good understanding. So it's a method of adapting the synthesis, right? So yeah, check this. Isomers, optical. Explain the relevance of chirality. What are enantiomers? Identical physical and chemical properties apart from their ability to rotate plane polarized light and their potential biological activity. What is a racemic mixture? It is a mixture containing an equimolar amount of each enantiomer. So what is the relevance of chirality? The potential different biological activity need to separate a racemic mixture. Use of chiral catalysts to produce a single pure optical isomer. See, it's all in the syllabus, guys. So yeah, the answer should be use a chiral catalyst. Perfect. We're almost at the end, guys. We don't have much left. Predict the number of peaks that would be seen in the carbon-13 NMR of tolubutyral. Okay, carbon-13. Let's do this. Carbon-13 totally depends on symmetry. So the compound on the left isn't actually symmetrical. Okay, it isn't symmetrical. Sadly, it does not have a line of symmetry. However, these three guys, these CH3s are the same because they are in the same environment, right? If you go from here to here, you will get to the same carbon, and then if you go here, you go to the NH. So I am going to consider this one, and this one to be environment A. Next, this carbon is unique, it is environment B. There is no carbon like this, it is environment C, okay? Because it's unique, no one is like this carbon. It has an NH on the right and OH, CH, OH on the left. Now this carbon is also unique because it is directly attached to an OH. There's nobody like this one. Now if we go next, this carbon is unique, right? There's nobody like this one. So why don't we use numbers instead? It's going to be easier for you guys to follow. 1 1 1, same environment. Environment 2, environment 3, environment 4, environment 5. Now this carbon is also unique because it's attached to chlorine directly. Now comes the hard part. This carbon is unique because look, if you go here you get chlorine, right? But if you go from this carbon you do not get chlorine, you get a C followed by CHOH. So the one below is unique as well. That's the hard part, right? So this is actually 8. Now this is 9 and this finally is 10. Okay, so it was hard. How could this compound be different? What if, guys, we had a compound like this? Okay, check this out. OH, NH. So these would be 1, this would be 2, this would be 3, this would be 4, this would be 5. Now since this compound is symmetrical, these two would be 6, these two would be 7, and this would be 8. It would have been 8 instead. But due to the addition of this chlorine here, it's not symmetrical, and as a result the compound has a lot of unique carbons on the left hand side. Hopefully you guys could understand my logic. Okay, so it's going to be 10 clearly. The proton NMR of tolubutyl dissolved in D2 shows peaks in 4 different types of proton environments. Okay, so let's do this. Tolubutyl. How many proton environments does it have? Let's do this. Come on. So proton environments. Step by step. Okay. So these CH3 groups, they are environment number 1. Now this carbon over here has no hydrogen, so no environment. This one is environment number 2. Then what do we have? This one is environment number 3, this CH2 unique. This one is environment number 4. This one is environment number 5. This one is environment number 6. Actually, remember that all in carbon NMR, like the carbons in the benzene ring are unique, but in proton NMR, the carbons in the benzene ring are all in the same environment actually. So in a normal solvent like CdCl3, there are 6 proton environments. Okay, I can draw another compound to help you guys. This is the normal version of tolubutyl. CHOH, CH2, NH, C, CH3, CH3, CH3. So all these 3 environment number 1, this one 2, this one 3, this one 4, this one 5, and all of these are in environment 6. Now, by the way, sorry, when I mean all of this, basically you guys know that there's no hydrogen over here, right? It's been substituted. So these 4, basically, these 4 are in environment 6. These 4 over here, 4 carbons. Okay, anyway, after we add D2, 2 of these peaks disappear. You guys know why, right? Basically, the proton of NH and OH, they're actually labile, so they exchange with D2. Okay, so you actually end up with this afterwards. This actually, these 2, right? They turn into OD, O, just D over here. As a result, instead of having 6 peaks now, how many do we have? We actually have 4 in total. 1, 2, 3, 4. That's it. That's what they were saying over here. The proton NMR of tolubutyl is dissolved in D2O. Now it shows 4 different types of proton environments. The peak for the CH2N environment is a doublet. Now let's try to find out the types of the peaks. This is also important. Basically, guys, if you're attached to electronegative atom, you're gonna be a singlet. This was singlet. This was a singlet. Now this guy over here, this is a very tall singlet because the adjacent carbon, this carbon over here, does not have any hydrogen atoms, so no splitting. Okay. What about this one, this CH2NH? Basically, we will not consider hydrogens on the right because it's attached to an electronegative atom, but on the left hand side there's one hydrogen, so 1 plus 1 is 2, so it's actually going to be a doublet. For this one over here, I'm not going to consider the upper one because it's connected to an electronegative atom. On the right hand side there are actually two hydrogens, so 2 plus 1, we actually get a triplet, and on the left there's no hydrogen, right? And for benzene ring, always remember that benzene ring hydrogens always result in multiplets. Okay, so this is the, in general, this is the trend. So after addition of D2O, we still get the same. This is a singlet, this is a doublet, 1 plus 1, this is basically a triplet, and this is a multiplet. Okay, fine. So what's the question? Actually, I've analyzed it. The peak from the CH2 N environment is a doublet. Fine. CH2N is a doublet. I wrote that on the right. In the chemical shift range of 2 to 3 ppm. 2 to 3 ppm. CH2 attached to an electronegative atom. Alkyl next to electronegative atom. Alkyl amine basically. 2 to 3 range. Fine. Now give details for each of the other three peaks in the Proton NMR of tolubutyl. Fine. So what are the other three? The multiplet, the singlet, and the triplet. Okay. So we need to mention the chemical shift, the environment of the proton, the splitting pattern, and the number of hydrogen atoms responsible. So let's do this step by step. Here the number of hydrogen atoms are 9 hydrogen. Here it's actually 2 hydrogen. Here it's 1 hydrogen, and here it's 4 hydrogen, right? So let's begin. Let's start. So let's do the benzene ring first. Benzene ring. You guys know that for a benzene ring, where is it? Attached to aromatic ring, it's 6 to 9. So for a chemical shift of 6 to 9 range, we have 4 hydrogen over here. It is a multiplet, and it is mainly due to hydrogen attached to AR, like in the data booklet over here. Hydrogen attached to AR, look, HAR. You could write that, or just say that it's attached to hydrogen attached to aromatic ring. Fine. Next, let's go from left to right. Okay, let's talk about the triplet. Okay, the CH, it's actually connected to an oxygen, or it is basically connected to the aryl ring. Anything works, but the oxygen actually gets priority. Okay, the alkyl next to an electronegative atom, oxygen. Alkyl next to electronegative atom, this one. Okay, so that's it's a CH connected to O, so the value is actually in 3.2 to 4 range. So chemical shift of 3.2 to 4 range. How many hydrogens? 1 hydrogen is responsible. It is actually a triplet, I already taught you guys, because the adjacent carbon has 2 hydrogens, and it is basically a CHO, or alkyl next to electronegative atom. Okay, last, the one on the right, the CH3, triple CH3, yeah, triple CH3. So chemical shift of how much? It's basically connected to, it's just an alkyl, it's the lamest one, just an alkane, yeah, just an alkane. It's CH3 connected to C, alkane, 0.9 to 1.7, yeah. So chemical shift of 0.9 to 1.7, mainly responsible 9 hydrogen atoms. Okay, and I taught you that it's a singlet because the adjacent carbon does not have any hydrogen atoms. So we are going to say it's 9 hydrogen atoms are responsible. It's a singlet, and it's basically a CH3 or just alkane that works. See if you guys understood. It was a bit tricky. Yeah, it's not for everyone. You had to analyze the question first before moving on to it. Okay, 22 marks. There you go. Moving on to the last and final question. It has been a wild ride. It's already 2 hours 14 minutes. Oh my god, this is a 2 hour 30-minute video. This is why I don't want to solve chemistry paper 4, because there's a lot of explaining and it doesn't get enough reach. So please support the channel, guys, if you like the content and want more P4 videos. Okay, I plan to do ON 2022 and May June 2022. I had one variant remaining. Those three before your May June session. 4th May. Let's hope for the best. A student uses TLC to analyze a mixture containing different metal cations. The student repeats the experiment using different solvents. Figure 6.1 shows the chromatogram obtained by the student using water as a solvent. So just a compound that could be used as the stationary phase in this experiment. Fine. So this is thin layer chromatography. So we know that it's either silica or alumina. It's ingrained in the, it's heated and ingrained on the chromatography paper. Yep, that's how it works for thin layer chromatography. There's a thin layer of silica or alumina which tries to prevent the pigments from moving or the cations from moving. The table shows the RF values of different metal cations when separated by TLC. So it's the identity of the cation that caused the spot at M. Guys, M. Check this. M is at 2. So guys, the solvent front is at 5 and M is at 2. So let's find out the RF value. 2 by 5, how much is it? 2 divided by 5 gives you a value of 0.4. So clearly, M is this compound over here, CD2 plus, yeah? CD2 plus. Why? Because the RF value is actually 2 by 5, which is 0.40. Fine. The student repeats the experiment using butane 1-ol as a solvent. The metal cations do not travel as far up the TLC plate in this experiment. So that's why the metal cations do not move as far up the TLC plate with butane 1-ol. So basically butane 1-ol, we used water before, right? Now we're using butane 1-ol. So butane 1-ol is an alcohol. These cations were very soluble in water. The more soluble you are in the mobile solvent, the further you will move. But if you're less soluble, you'll move less far. Okay, so basically the metal cations, they're less soluble in the mobile phase now, are less soluble in butane 1-ol than in water. Okay, fine. The student sprays the TLC plate in figure 6.1 with KSCN. The color of some of the spots changes as some of the metal cations undergo ligand exchange reaction. Identify the ligands involved in the ligand exchange reaction. So KSCN. What is this basically? Potassium and SCN. This is the anion. So what's the water with all these, what's the ligand with all these cations? It was basically, remember, CdH2O6, something like this basically. So basically the ligand water or is exchanged, right? So by which anion over here? This SCN anion. The SCN anion exchanges with H2O. That's what happens basically. Okay, because K plus is not a ligand, you guys know that. So what's remaining? This SCN part. So that's the ligand, the possible ligand with the lone pair. And you know that there was water over here, so water is exchanged. SCN exchanges with H2O. Fine. Okay, moving on to the last part. In the third experiment, the pH of the mixture of metal ions is kept constant using a buffer solution. The student prepares the buffer solution by mixing 20 cm cube of 0.1 mole per dm cube KOH and 50 cm cube of 0.1 mole per dm cube C8H5O4K. C8H5O4K is a weak carboxylic acid that has a pKa of 5.4. Complete the equation for the reaction of this with KOH. It is actually, you know, it's supposed to be a dioic acid, but one of its acid parts is actually taken up by potassium, right? So it is actually a monobasic acid. It can only release this OH. So it's going to be a 1:1 reaction, okay? Because one of the potassium, one of the H plus is already occupied. So it reacts with KOH to form this. This H will be taken away and it's going to form O minus K plus here as well. So C8 H will reduce by 1 to H4, O4 will remain the same, and this will turn into K2. Okay, and we are going to get 1 molecule of water. Calculate the pH of the buffer solution and show all your working. Okay, so we have the formula over here, we have the reaction over here. Okay, so you guys know what's gonna happen. Initially, what did we have? Initially, the moles of KOH was, this 20 by 1K times 0.150, which is 3.0 into 10 to the power minus 3. And what about the moles of acid? It was actually 50 by 1K times 0.100, which gives you a value of 5.0 into 10 to the power minus 3. Fine. So initially, let's write this equation over here, then it's going to be easier for you guys to follow. C8H5. So there was actually a question like this back in February, March 2021. I would recommend you guys do that. Anyway, so C8H5O4K reacts with KOH to form C8H4O4K2 plus H2O. So what was the initial moles and what was the final mole after equilibrium? So we had 5.0 into 10 power minus 3 moles of this and 3.0 into 10 power minus 3 moles of this. After equilibrium, after they reacted, since they react in a 1:1 molar ratio, all of the base will be used up, right? And some of the acid will remain at equilibrium. So this becomes 0 and this turns into a 2.0 into 10 power minus 3 after subtraction. And since this also has a 1:1 ratio, this was 0 initially, now it will increase to 3.0 into 10 to the power minus 3, okay? And also water 3.0 into 10 power minus 3. That's worthless though, we don't need that. Okay. Fine. So let's do this. Now at equilibrium, what do we get? This is a salt, right? This is the salt. So moles of the salt Ka is actually also 3.0 into 10 power minus 3. It will increase by the same amount. And the moles of the acid Ha is actually 5.0 into 10 power minus 3 minus moles of NaOH 2.0 into 10 power minus 3 because they react with in a 1:1 ratio. Sorry, 3.0 into 10 power minus 3. Yeah? We get a final answer of 2.0 into 10 power minus 3 as I've written above. Now you have two options. You can either use the Henderson-Hasselbalch equation, which they don't use these days. I can still show you, or you can just go for the Ka route. Okay, so let's go for the. Oh no, they actually use the Henderson-Hasselbalch equation after a long time. Ah, interesting. Okay, so I'm going to show you both ways. Okay, so firstly, using the Henderson-Hasselbalch equation, we know that pH is equal to pKa plus log base 10 acid. Okay, so there are a lot of variations. I'm going to show you. Like there are two variations of the Henderson-Hasselbalch equation, or you could just go for the Ka route. Okay, so if you opt for the plus sign, wait, let me show you. This is best if I show you. Wait, one sec. Last question. Yeah. So If you opt for the plus sign, it's going to be log plus log base by acid, and if you opt for the minus sign, it's going to be minus log base 10 acid by alkali or base or salt in the context of this question. So this was the question I was talking about. The last question, number F, aces. Do this afterwards. Really important question. I think I have this solved as well in my channel. I'm gonna link that um, at the end of the video. You can check that out. But it follows a similar concept, okay? But they didn't use the Henderson-Hasselbalch equation back then, but now they've reverted to using that again. All right, so pH is equal to pK. If I use a log plus log base 10, I have to use the salt above. Okay, I have to use the salt above, which is Ka or A minus divided by the acid, the concentration of the acid. So what do I end up with? pH is equal to, what's the value of pK? It is a 5.40, as you can see over here. So that's 5.40 plus log base 10. What is the concentration of the salt? It's basically 3 into 10 to the power minus 3 divided by a 2.0 into 10 to the power minus 3 acid concentration. Let's do this. Also, yeah, its concentration, I know that this is the moles, and what is the net volume? 50 plus 20, right? We have 50 plus 20 cm cube, which is 70 cm cube. I do get that, but that actually cancels out. Okay, so 70 cm cube by 1000 is 0.070. There's both of them are divided by this, so it actually cancels out. So that's 2 into 10 to the power minus 3 divided by 0.070. Okay, so we get rid of these, and at the end we end up with 5.40 plus, wait, let me check, 3 by 2 log base 10, answer 0.18176, 0.18. So we get a value of 5.58 minimum 2SF. So that's root 1. This is root 1. What about root 2? Root 2 is almost the same. Its pH is equal to pKa minus log base 10 acid by salt. This also works. So pH is equal to 5.40 minus log base 10. Basically 2.0 into 10 power minus 3 by 0.070 by 3 into 10 to the power minus 3 divided by 0.070. So that will give you the same answer as 5.58 as well. Okay. Now, what about the last approach, which is a bit different, which they've started recently, basically, the Ka method. So we know that pKa is equal to 5.40. So Ka is actually equal to, you know that pK is minus log base 10 Ka. So 5.40 is equal to minus log base 10 Ka. So Ka is actually equal to 10 to the power minus 5.40, right? So can we write this, that Ka is equal to, for the dissociation of this acid, essentially, we can write that it's H plus, right? So suppose this is the acid, right? It's basically like dissociating the acid over here, C8H5O4K, this weak acid. What is it? C8H5O4K. C8H. Wait. Give me a sec. C8H5O4K. So what happens to it? It dissociates to form H plus and C8H5, sorry, H4, C8H4O4K minus. Okay, this is what happens. So you can actually write this equation above as basically like this. HA dissociates to form H plus and A minus, yeah? So H plus into A minus divided by the concentration of the acid itself. This is one logic. Okay, so this is it. Now you could input the values like 10 to the power minus 5.4 over here is equal to, what do we need to find out? We want to find out the value of H plus remaining. Now we know that the concentration of the salt, or A minus, is basically 3.0 into 10 power minus 3, yeah? So the into 3.0 into 10 to the power minus 3, and the concentration of the acid remaining is 2.0 into 10 to the power minus 3. I personally do not prefer this method, but they've recently started using it. So the concentration of H plus is actually 10 to the power minus 5.4 times 2 into 10 to the power minus 3 divided by 3 into 10 to the power minus 3. Okay, that gives you a value of 2.65 into 10 to the power minus 6. Now you know that pH is equal to minus log base 10 H plus. So use your calculator answer. Minus log base 10 answer gives you a value of also 5.58. So that's option number 3. But yeah, go for Henderson-Helsenbeck equation because it's much more easier, right? Okay guys, that is the end of this question paper. I wouldn't say that it was a very hard question paper because like most of it was easy. Okay, but a few parts, like around 15 to 30 marks, 15 to 20 marks, were very hard. You had to think a lot, especially this last pH sum, and the one with this buffer, and then some other questions, this 1 mark question over here, right? Some it was tricky. The NMR, you had to do a lot of analysis. I haven't seen a question like this for a long time. Okay, then we had this new part over here. But yeah, overall the end was a bit tricky. So advice for going into the major 2023 exams is that just go through the mark scheme for 2022 and 2023 specifically. Learn the mark scheme, learn how they want the answers, and just, yeah, good luck with your exam. And I'll solve more October November papers soon, very soon. Okay, I'll try to upload them within 1 to 2 weeks. Okay, so I'm gonna link the paper for Feb March 2022 paper 4 2 up here, and the paper for Feb March 2021 paper 4 2 down here, and the playlist for chemistry P4 up here. And hit the subscribe button if you like the video. See you guys.